Okay. Yeah, so I'll write up the metrics again. That's the questions I introduced later. So let's start. So the first, before going on to the next subject, I had a little remark that I forgot to mention. That will actually be important later. So this is something about what's called killing horizons. Because the statement is that all stationary, so including static black holes, black hole spacetimes, have a particular killing vector field which is null at the horizon, the event horizon. So it means that for any stationary asymptotically flat spacetime, you have a vector field. There exists a vector field K such that it's a killing vector field. So we have killing equation to base. And if we compute the norm with respect to the metric for this vector field and evaluate this on the event horizon, then we should get 0. So this is just more mathematically what this means. So the statement is that any stationary asymptotically flat black hole spacetime have such a killing vector field, and it's up to multiplying with a constant. It's unique. This can also be turned around into a definition of what you mean with the horizon. And then you introduce something called killing horizons. So basically, a killing horizon for a killing horizon, what we call a killing horizon is defined as a null hypersurface somewhere in your spacetime for which you have a killing vector field that is null everywhere on this null hypersurface. That's the definition of a killing horizon, and then you can show that, well, first of all, you can show that the event horizon is a killing horizon in this sense, but you can then also show that a killing horizon is an event horizon. That's the harder step. And this is important when you want to work on the mathematics of black holes. That gives a more precise definition of event horizons. Anyway, so for the Schwarzschild black hole, you can see that you can take this killing vector field to be just the time translation vector field. And you can then see that we have these t, x, y, and z Killing vector fields or any linear combination of those that gave us all possible Killing vector fields structure. But then you can see, I mean, if you take an arbitrary linear combination of those, right, you can see that this, or a constant multiplied with this, is the only one for which k squared, so t mu, k mu, nu is 0 at the integral, right? Which the x, y, z doesn't give anything. Yeah.
So in your definition of filling horizon, you haven't actually specified any condition on the event horizon. So could it just be generically any surface at all in the space-time? But that also said just a flat surface.
Well, no. I mean, it has to be a null type of surface. So, which means so you have a function that defines your maybe I had something. Okay, so this is the only this or any constant multiplied by this is the only one that satisfies this requirement that it's no longer horizon. So if you instead take the curve record, then you find that there's a specific linear combination of the two Killing vector fields that we found, where this is something very specific, namely this in terms of the parameters of the curve. And then you can find that for the specific linear combination again, this is satisfied. If you look at the Schwarzschild, just to take the easy example, in this case, this is in these coordinates, this came just like this, right? So the coordinates G are, so this is just G0. And you can see that this is 0 for R. So, and something similar here. Just the algebra is more complicated. Okay. Any questions to this? So this I will use a bit tomorrow at some point. Okay. Then we go to something rather different, namely to render space time and surface gravity. So what we basically want to study now is how does the metric look close to the wind horizon? And we start with Schwarzschild since that's the easiest. So right now we only discuss Schwarzschild. So we want to look around r equal r0, right? Where the event horizon is. So therefore, we write r in terms of another coordinate which we call x. So like this. So r0 and then 1 plus x squared over 4 r0 squared. And this looks strange, but it will be more clear. I hope why I chose this coordinate. And then we want to look at when x is very small with respect to r0. So this is what defines to us being close to the horizon. So first, let's try to look at this, which goes into the metric over there, and insert this definition of the x up here. So what do we get? Well, this is just a simple algebra. So here I just insert the definition, right? And now I can approximate this. So we expand this below, and we get just that the ones go out, and then we just have x squared over 4 r0 squared. So that's the leading direction, right? Then we can compute the r squared. So the r squared, we have to differentiate. So this is just a constant, and then there's a 2 there. So it's r0 times 2 x dx over 4 r0 squared. So then the whole thing squared. Right? So then it's 1/2 x squared over 4 r0 squared. Okay. So using this, we now insert these two results in the metric, and it's so beautiful here, but I'll try. So how does the Schwarzschild metric then look close to the horizon? So the first part is this x squared over 4 r0 squared to t squared. And then there's a dx squared, which is because if you look at the dr squared, then it's this divided by that, right? And then for the 2 sphere part, it's just we're close to the horizon, so r is actually equal to r0. So what is this? Well, this part here we recognize as a S2, I mean a 2 sphere, or sphere if you want, with radius are zero. And this is what we call the Ringler spacetime. So it's a two-dimensional spacetime. And part of understanding black holes is to understand this two-dimensional spacetime. So okay, so we can to understand this a little better, we try to consider a static particle that lies at constant value of x, with x greater than 0, outside the event horizon. And with static we really mean in this coordinate system, so with respect to this time and so on. So it's specific for this coordinate system or this one. Right. So then we want to compute now. Well, let's first. Well, if we first look at the velocity. Because we want to compute the acceleration in a moment, so we first have to understand the velocity. So the velocity, since it's static, has only one component, only the time component. But since we are not in Minkowski space, this is not just one, because you always have that velocity vectors are such that the norm is -1, right? So the norm being -1 in this case then means that GTT UT squared is equal to -1, and then you can look at this GTT here and see that means that UT has to be equal to 2 R0 over x. Okay. So then we want to find the acceleration. So what is the acceleration? It's the acceleration with respect to the proper time. So this is the proper time of the particle that we are looking at, this static particle. And so this is equal to this, just by the two, where this is the invariant derivative in 4 dimensions, and this is actually nothing but the velocity vector, right? So you see that this is how I define the velocity, sorry, the acceleration in terms of the velocity vector in this case. So in this case, there's only the time component. So we only have to worry about the invariant derivative in the time direction. And then it should be very familiar to you that we then need the distortion symbol. Like this. And then, so then, again, this is only non-zero in the time direction. And this is actually just 0 because nothing depends on the time, right? And then we also need to put ut is that looks like because then you get a ut there also. Yeah, okay. So the acceleration for a static particle is given like this in terms of the Christopherson. And then we just have to compute this Christopherson symbol. That's of course a very well-known thing. So you see that actually G is equal to 0. But the x direction of the Christopher symbol is not equal to 0. Because here we get derivative with respect to x of t from this, and if you take that derivative and plug everything in, we get x over 4 plus 0 squared. So okay, so we had this. Ut squared, this is 4 plus 0 x squared, and then this is x over 4 at 0 squared. So all together we get 1 over x. And sorry, yeah, I should have said sorry. This is like in the x direction. So at is 0 and ax is this thing that just works. So the acceleration in the t direction is 0 and the acceleration in the x direction is 1 over Okay. So the first thing you notice here is that the particle seems to accelerate actually away from the event horizon. So that could sound very strange because usually you are used to the particles trying to go into the event horizon. But the reason, of course, here is that this is not a geodesic that we're describing. So what we're describing is a particle which we are forcing to stay at a certain point outside the event horizon. And this means that we have to exert a force away from the pulling it away from the event horizon. And that's why the acceleration points away from the event horizon. Right? So it all is very natural in that sense. And then you can also see from this that if x goes to 0, so if it goes closer to the event horizon, the acceleration gets bigger and bigger, which you can say that makes sense because it takes more and more. You would think that it takes a bigger and bigger force. Right? But this is actually not the whole truth, even if it sounds very intuitive. Because here the acceleration we computed, if you remember, was with respect to the proper time. So if we instead try to consider what is the acceleration from an observer away from the static particle. So it's not this guy's or whatever astronaut, I don't know, sitting at the static part where the static particle is that observes it, but maybe somebody infinitely far away from the black hole, or very far away. So let's say instead, what happens if the observer will have proper time t instead of the proper time of the static particle. So somebody sitting far away from the black hole and looking at this static particle. What acceleration will he see the static particle having? Well, that's easy, right? That's just we just simply say the acceleration with respect to the time t is just this correction factor times the acceleration we just computed, because instead of this being with respect to proper time, it's just with respect to the time at infinity, right? And then we have to insert what is the proper time differentiated, the asymptotic time. And that we know because the proper time is simply given by this. So E tau is simply x over 2 plus 0 t, right? So using this, we just get that this is x over 2 plus 0, and then times what we just computed, right? So t is again 0, and ax t is now this times 1 over x, which is now 1 over 2 plus 0. So you get that there's still an acceleration which points away from the black hole, but now it doesn't grow as you get closer to the event horizon. So seen from the observer very far away, it doesn't look like to him like it takes more and more strength to escape the black hole, or whatever you can call it, not escape the black hole, but keep from falling into the black hole, I should say. Rather, it's the same force. Of course, this is computed in approximation where we are close to the event horizon. If you then took the full metric and all that and went far away with the static particle, this would change. But this is only true close to the event horizon. So therefore, we define this. So, just to summarize, this observer sees the particle as having acceleration 1 to R0. Double time. And we know that acceleration and gravity is one and the same thing, an equivalence principle. Therefore, seen from the observer from infinity, we can think of all this as the black hole geometry near the event horizon as having a gravitational pull of this magnitude. So this is something you call the surface gravity of the black hole. We usually write it as kappa surface gravity. So for the Schwarzschild black hole, the surface gravity is what we computed as 1 over 2 R0. So the surface gravity is just another name of the acceleration of a static particle here. Any questions to this? And this surface gravity is something you can, sorry, one second. So it's something you can define for any event horizon actually. That's why it's important, because it's something you can observe for any event horizon. Yeah.
The color black hole, the R plus and R minus, which would contain this one.
Yeah, so the event horizon is at R plus, the bigger. So I will take R plus. Then, but I will come back to the curve black hole. Yeah.
You said that this is surface relative for any, but it's different kappa.
It's different.
We have different kappa for carry.
Yes. I will actually try to compute it later. Yeah. Okay. So let's. But before I go to the curve black hole, I just want to have one more comment on the square space-time. Because so 2D window space-time, we can now write it like this. Because you can see this is precisely the surface gravity, well, not the x squared part, but the other part is precisely the surface gravity squared. So we can write it like this in terms of the surface gravity. Then you can define 2 coordinates, and I apologize that it's the same notation I used for the Killing vector fields, but there's no connection. This is coordinates. So if you define these two coordinates, then in these coordinates the same metric will look just like this. So you see that this is two-dimensional Minkowski spacetime. And what does this mean? This means that actually the regular spacetime, which has this acceleration we saw before, is nothing but what accelerating. I mean, regular spacetime is the spacetime an accelerating observer would see in the Minkowski spacetime. So an accelerating observer in Minkowski spacetime sees the regular spacetime. This is like a uniformly accelerating observer with constant acceleration. So in some sense you can say that the regular spacetime is sort of pure acceleration in that sense. And this also means that that one can define something for the acceleration horizon, and in some sense, then the event horizon is an acceleration horizon. Okay, so if you now go to the curved black hole, you can do the same thing by actually it's just algebraically more complicated. So what do you have to do for the curved black hole? You introduce something called co-moving coordinates. Which means you sort of move together with the horizon, as we will see in a moment. So you define a new time and a new angle, rotation angle, like this. And then we just have to compute how does the metric look in these coordinates. So you take the metric over there, and you start writing. It's a little long. I hope it's readable. Okay, so that's the metric you get. Yeah, and then you can compute then you can try to compute first t tilde by tilde. So looking at this, you get this thing here. But this all looks very complicated. Maybe one can say what's this good for? But if you now try to look at this at the event horizon, so at I equal R plus, and then stare at this a little bit, then you see that this is actually 0. So what does this mean? This means that in these co-moving coordinates, the horizon is not moving when we get close to the horizon. So that means that in the original coordinates, with the original phi t coordinates, that conversely means that the horizon is moving, and it's moving with precisely that angular velocity. So it means that this omega that we wrote here is the angular velocity of the event horizon. Then we can also try to compute t tilde t tilde. This is another long expression. Now we want to get back to this windless space thing. So we would like to see how does this look close to the event horizon. So for that purpose, we do like we did with Schwarzschild, namely introduce these. We introduce a new coordinate instead of the radius. Which we again call x in this sequence plus square, b square, square. And then I should say that we are considering here failure then we also have that this delta function r minus r0, r minus r plus, that is now approximately r plus minus r0, or sorry, r plus minus r minus r plus. And then you can insert, and you can put this r. So what do you get? So you have to compute now. One thing you have to compute is this in front of the r coordinate. This here. Well, there's a lot of algebra, and then you get in the end dx squared by virtue of this choice x. Just by inserting points. Then an even more complicated computation is the GTT, or rather G tilde, T tilde. Near the event horizon. And I think I'll skip the computations. You just take all this, you plug in this, and what I wrote here, and then you compute. So, unless somebody wants to see it. Okay, so the result is the following. Okay. So this means that I can write the Wendler space. I mean, I can write the Kerr black hole now for let's just say near the event horizon. Yes, it's something like this. So you can write the metric near the event horizon. Minus kappa squared x squared t tilde squared plus dx squared. And then plus the angular part, which for now I won't write. That is also there. And where this kappa you can read off from here. So kappa being the surface gravity is just r plus minus r minus over 2 r plus squared plus a squared. So then you get the surface gravity for the Kerr black hole. Any questions today? Let's take a 15 minutes break. I mean, unless there's questions.
So the
Yeah.
the other term, metric in your bracket, it's what kind of metric?
Sorry, which term?
The term you
Yeah.
here is what kind of?
I mean, it will be.
That
I mean, it's the equivalent of this yeah.
so what?
It's some metric. You know, it's the metric for the angles. You know, the phi.
So it's also a
theta and
sphere.
phi angles.
So it's also a sphere, or
It's actually not a sphere. That's why I'm not writing it, because then I'll just write it. But it's not a sphere, because the curved black hole is. You know, the more it rotates, the more sort of flat it gets. So it sort of becomes more like in if you could take the really highly rotating limit, then it would be more like a pancake. But it actually, the rotation is up and down. So it's not a, it's a more complicated metric. So that was right. But I mean, well, what you do is you just take you know, this term here, this term here, and then you insert that R is equal to R plus, and you write it down. It's not intuitive in that sense. Okay, so then let's take a break. So we have one more quantity we'd like to define for black hole. I mean, if you remember, we have defined the mass and angular momentum earlier this morning. And in analogy, you could also define the charge. I haven't done it, but all these, all three are defined for black holes in analogy with Newtonian matter. Then we defined two other quantities so far, namely the surface gravity and the angular velocity. So the angular velocity you can also define for the Schwarzschild black hole, but it's just zero because it's not moving, it's static. Right? So the angular velocity is just zero for Schwarzschild, but it's equal to I guess I deleted it. Something for the curve as it's this. Right? And then we have the surface gravity also, which we also found both for the Schwarzschild and the curve. And now I would like to find another quantity, namely the area of the event horizon. But actually, one other thing just before I get to the area of the event horizon, just wanted to say, I mean, with this Ranger space, right, let me speak. I go on to the area. So area of event horizon. So what we found is that, say for the Schwarzschild, we found that the space-time looks approximately near the event horizon like this. So this was the render part, and this is a two-sphere with radius R0. Right? So if you have a two-sphere with radius R0, it makes sense to, you can compute the area of the two-sphere. So this would just be 4 pi R0 squared. Right? That's the area of this sphere. And this I should say, this is if t is constant, so you're looking at a particular time slice, and also x is equal to 0. In the sense that, if t is constant, then this term is absent, and if x is 0, then actually both terms are absent from x equals 0. Then the only part of the space-time you have left is this part. And then you can compute sort of the area of that part, which is just a two-sphere.
Does that require x equals to 0? Just x has to just be fixed to be something small.
Yeah, well, but then you can say then there's a small convection, because then this is really, r squared here. Then it's like plus a correction. So the exact area of the event horizon is when x is 0. And this you can generalize this way of thinking to any event horizon. Namely, this that you take a constant time slice, and then you set the radial coordinate to be at the event horizon, or whatever coordinate you have, and then you compute the volume of the remaining space that you have left. Right? So we can also do it for the curve, and for the curve. We have to again use these co-moving coordinates, and then, as I wrote here, then you can write that this is just. I will not write what it is specifically, that you have to work out yourself. Right. But near the event horizon, the metric has this form. So there's some function here of this is only a function of theta, and also this is only a function of theta. There's some function of theta here, and some function of theta there, and that gives you a metric for whatever ellipsoidal geometric object you have. Okay. And then you can just do the same, so as you did for the Schwarzschild black hole. So you say we want to be at the event horizon, so x is equal to 0, and then we take a constant time slice. And then the area is the volume of whatever you have left of your metric. So this is simply the integral for the two angles that you have. And then this part here. evaluated at the event horizon. And also T equal the constant doesn't depend on T. And then one can actually find out that, yeah, I already implemented that. I should have written tildes here, but actually, at the event horizon, T tilde is equal to, sorry, T by tilde is equal to T by 5. And then all you have to compute now is, you insert now what this times that is with the event horizon, and then you compute. And so it's 2 pi, and then equal over theta. And then I computed the product here, which is plus squared plus a squared sinus phi, and then you compute the integral, and then it gives you so then it gives 4 pi plus 0 and plus. So this is the area of the event horizon of the curve black hole. It's defined in this exactly the same manner as the Schwarzschild black hole. And all this is again using this approximation of the metric near the event horizon. So we have a new quantity for the black hole. And why is this new quantity important? Well, it's important because there's something called the area theorem. So if you take the area theorem, this is by Hawking's area theorem. This is, we defined it more abstractly for any event horizon. So, I mean, also with all possible matter fields, whatever you can imagine. So this theorem states that the area of the future event horizon of an asymptotically flat spacetime is a non-decreasing function of time. That time then means this asymptotic time. So this is a statement which you've understood as a statement about dynamics of classical general relativity. So it's not something that applies to situations where you include quantum effects. So not necessarily. So if we now look at the Schwarzschild black hole, then you can compute for the Schwarzschild black holes 4 pi r0 squared. So this is actually 16 pi g squared m squared if I write it in terms of the mass. That's the area of the Schwarzschild black hole. So suppose now we take a situation where we compare two event horizons with one event horizon. So, and we do it assuming that we have the same total mass. So in one case, like in the case down here, we just have this where m is m1 plus m2, and up here we have the area m1 squared plus m2 squared. So because there are two disconnected event horizons in the area, we just add up the areas of the event horizon. Sorry, but yeah. And then we can see that this is always bigger than that, right? Oh, sorry, it's the other way. Yeah, sorry. This is always bigger than that, right? And that means that since the area of the event horizon is a non-decreasing function of time, it means that it's allowed to go from here to here using the dynamics of classical GR. That is something possible in GR. But it's not possible to go the other way. So somehow built into GR, there is some sort of arrow of time, like in thermodynamics, where you have a dynamics which is irreversible, right? So you can work GR one way but not the other. That is, in physics you are used to linear theories, right? So yeah, you can write it like in quantum mechanics. You can always go both ways in time, right? You just take a unitary operator and then invert it. Then you go the other way. But in GR, you actually have situations where you can only evolve one way but not the other. This because it's a non-linear theory.
Even if you change t by minus t, I mean, that's a symmetry of structure.
Yeah, that's true. Yeah.
But situation one is not symmetric.
Yeah, exactly.
Sorry, what?
This is true for just if you can step one. Right.
So one is not a slice symmetric. Two slices.
Yeah, no, it's not a symmetry. Sorry, thanks. Okay. So this is a irreversible process. Merging two black holes into one black hole is a irreversible process. The other thing one could think. So this is true, but then you could think, but maybe this means that. So let me put it as a question. So does this mean that mass never decreases. Because you could think that this sort of means that you can only absorb matter, you can never get matter out of the black hole, basically. And therefore, the black hole somehow always, I mean, not only the entropy is a non-decreasing function, but also the mass must be non-decreasing. But this is actually not true. And the way to see that is to look at the so-called Penrose process. And this is something where it's important that the Kerr black hole has something called the Ergo region. So the Kerr black hole has a region where GTT is greater than 0 outside the event horizon. You know, normally GTT would be less than 0. But it has a region outside the event horizon called the Ergo region, where GTT is greater than 0. And this Penrose played a bit with. So what he did was to imagine a process where a particle decay into two other particles. So you start with a particle A, and then somewhere in the Ergo region it decays, and out comes, let's see, particle C and particle B, but the fate of particle B is to go into the black hole, whereas the fate of particle C is to escape the black hole and go out to infinity. And then we know that there's, we assume it's an elastic process, so then we know that there's momentum conservation and energy conservation. And then we can see, if you now take I mean, if you want to define what we mean with energy, right, then asymptotically, this is our time translation generator. So energy, for that reason, means that we take the product of this with the momentum, and this gives us the energy. So P mu, right? And normally, under normal circumstances, this definition would ensure that the energy, wherever you compute it in your space-time, is positive, because if you take two negative norm vectors and take the product of those, then you can show mathematically that the product with respect to the metric is also negative. So this means that the energy is always positive, right? Which of course is a very nice thing. But in this case, we see that since the collision happens here, and since this B never comes out to infinity, and you can measure the energy out of, measure the energy out at infinity, and since T squared in here is positive, because TTT is positive, then it's possible to have a situation where the energy of this B particle is negative. Sorry, what was the...
I don't understand. What's this P squared, the distance in T squared? less than 0 from every
This thing, yeah. So this is just a mathematical statement. In which sense do you not understand it?
I mean,
Mathematically or?
I mean, if p squared less than 0 and t squared less than 0, also.
I mean, it's vectors, if that's what I don't know what your confusion relates to.
No, okay. It's also, I mean, this does, I mean, it's possible that pt less than 0, but it doesn't mean that it's always less than 0. It's,
Why not? Well, I can show it.
okay, but, okay. I mean,
Yeah.
you want to write this that scalar product of p and t and equals to, we have cosine that's p less than 0.
Let me show
Okay.
it.
I can
It is okay. And then you can see if we can find a mistake. You're right. So I want to show this, right? So I proved that by assuming that it's a positive or 0. And then I can always choose, since I'm only interested in looking at this at a certain point in my space-time, I can always choose at that point to have a local Lorentz frame. So I can always say the metric there is equal to the Minkowski metric, just by some format transformation, because it's only at that point. And then you can just write up so you have this, right? So this is the time component of B and A and B, and then you get that from these two inequalities, you get that means that A0 squared has to be equal to A vector squared, and B0 squared has to be equal to, so it has to be greater than B vector squared, right? From this. Then you can also look at A dot B. So this is equal to A0 B0 plus A vector dot B vector, right? So I assume that this is greater than or equal than 0. So this means that that A vector B vector dot B vector is greater than or equal than A0 B0. Right? And then that means that since A0 B0 are greater than these, then it means that if I take the square root, right, then it means that A dot B has to be equal than greater than equal than the norm between sorry, it's even more, it has to be greater than, because this is greater than the square root of, right? From this. Right? But then we know in we have a standard thing with norms that this is always less or equal than that. Right? The dot product of two vectors. So then this is the opposite. That
this here is that you, inside this point where GTT is greater than naught, you can no longer choose GBU speed if you do at a point. Is that clear? So the reason that this doesn't hold inside, which will it be?
Yeah, it's this part here that breaks down. This is still true, because this comes from, you know, you can always go to a local Lorentz frame, and then if you want a time-like trajectory, you know that the velocity is time-like, right? And then you know that u squared has to be negative, or u squared has to be negative.
But can I still do that inside this little region where GTT is greater than naught?
Yeah, because you can still define what you mean by velocity in here, right?
Yeah,
And then you can define everywhere. So what breaks down is this required, this assumption here, because this is using a definition of time. And there can be several ways to define time in a space-time.
So can we turn back about that? We had a question, does this mean that the mass never decreases? So then what we mean by mass? The mass of black hole?
Yeah, no, so let me get to that, because that was my conclusion.
Because we talk about the particle there, so
Let me say what my conclusion is. So the point of this is that since this breaks down in here, and this particle is a particle that we never see methodically, then we can have a situation where the energy measured in this way is actually negative. So EA and EC both has to be positive, but EB, since it never escapes to infinity, that is possible to tune this so that it's negative because of this. And this means that if you compute now the total energy before and after, right, then you see that the energy of the black hole must have decreased, meaning the mass of the black hole must have decreased, right? Because simply because the energy of particle A is equal to energy of B plus C, but this is greater than, smaller than the energy of particle C, since EB is negative, right? So that means that you get more energy than you started with. And there's only one place this energy can come from, and that is from the black hole. So you have extracted some energy out of the black hole in this process.
but this is not possible for Schwarzschild black holes, right?
No, because it doesn't have a average.
Yeah, so okay.
It's only for and you're gonna. It's always. In these processes, it's always true that the area either stays the same or increases in the process.
Also here.
Yeah.
Increases.
So the area for Turine remains. That is not the entropy increases or stays the same. And in the processes where you extract the most energy are the ones where the area stays constant.
Oh.
So that's the most efficient processes, right? In thermodynamics. Right? What else? Something else I wanted to say. yeah, also, in a way to understand this is that doing this process actually makes this black hole rotate. I mean, the angular momentum goes down in the black hole you have after the process. So you sort of take some rotational energy out of the black hole. That's a way to understand what's going on. So this is maybe the most. This is from I think from the 60s also, and this is the most up to state of the art back then. Because this is actually very surprising that you can extract energy from a black hole. But that also means that was a reason why the area theory was so important, because this sort of goes against your intuition for black holes, but then you know that the area theory always holds. So there is some way to understand that the black hole always gets bigger. But it's not the energy, it's the area that you should think of that always grows, at least classically. So then we are ready to formulate what black hole mechanics is. So what is black hole mechanics? Well, it's just some laws for black holes, and for now we stick to neutral black holes, so no charge. So we have these. We defined these 5 parameters for black holes, right? And then we have some laws for these. So there's a zeroth law, namely that the surface gravity is constant on the event horizon. Then there's the first law. This says that suppose we perturb the black hole such that there's a small change in all of these quantities during this perturbation, and then we wait until everything is settled down and you have an equilibrium again. Then there's a law for the change of all these quantities, namely this. And then finally the second law, that's this area theory. That the area is a non-decreasing function of time. So this, of course, well, let me first say that it's a good exercise to take all the quantities I defined and maybe hopefully you wrote them down or you can find them in some notes until I give my lecture notes. So you can take all the quantities for the Schwarzschild and the curve is of course the most interesting, and then you can try to see that the first law actually holds. But it's actually shown in a more abstract sense to hold as well, like where you don't really have to specify even a metric. So you can show it more abstractly using this concept of killing horizons. But anyway, more sort of down to earth approach is to just see that it actually works for the curve black hole, which is that the impact also works for the Schwarzschild, obviously. But anyway, so these 3 laws looks obviously I look like the 3 laws of thermodynamics. That's what we should get to now. Perhaps, or maybe tomorrow. But let me see. I think I start tomorrow with that. So tomorrow, as far as I understood, at 2:30, we go on with black hole thermodynamics. Okay, so any questions? Okay, so let's start here.